Okay, so these are annoying. And they're annoying because they're quite common in like the end of a Cal 1 course or the beginning of the Cal 2 course here. And so what this is an integral where you have some constant on top of a rational function and some irreducible quadratic on the bottom. And so we're writing that quadratic in the form ax squared plus bx plus c. And then, of course, we can't reduce it into some kind of factored form. There's no way to write it that way. So maybe there's a way that we can do this integral as like a general form and rip a formula for how to do this out of thin air that will apply to any integral in this particular form so long as it meets a couple of conditions. So first off, it should be noted that we're going to do this with all of the constants k, a, b, and c being drawn from the integer numbers. And that's just because if we do rational numbers or real numbers, then these constants get pretty ugly pretty quickly. So we want to use examples that are only drawn for integers. And so I'm only going to claim that this formula works for integer constants as opposed to real numbers or rational numbers or anything like that. Um, but it's a good challenge to see if the formula also gives correct answers for constants a, b, c, and k other than the integers. And I think it's pretty obvious that k can be anything because we have a constant multiple rule for integration, meaning as long as k is a constant of any description, it can be passed outside of the integral symbol. And so anything we derive with k on the outside will at least not have any problems caused by k so long as it's not zero. But of course, this would be very different if we were integrating something zero over anything. Okay, so to begin with, we'd actually like to make some notes. We'll do a little bit of algebra with the bottom portion of this just to try to make this a little bit easier to work with. So we can write this k on the outside so that we're actually working with the integral 1 over ax squared plus bx plus c dx. And then we'll work with this bottom term here. And we have this constant multiple rule for k out in front so that it doesn't have to be factored into this portion. So let's take a few notes about what ax squared plus bx plus c is. We know that ax squared plus bx plus c is a quadratic function. And of course, if a is equal to 1, then deriving how this thing can be written algebraically in an advantageous way for the integrand is pretty simple. But we'd like to do this where we have an a value that is not necessarily equal to 1. Well, to do that, we notice we have a quadratic. And so, of course, quadratics, if we were able to factor it, this makes us think of the ln of linear factors that are split apart by like partial fractions or something like that. And if this is unreducible and this one is supposed to be irreducible, then it makes us think that we might be able to get this to look like one of the inverse trig derivatives. And the one that we're specifically trying to get it to look like is the arctangent derivative. So what we like to do is rewrite this as a times x squared plus b over ax plus c over a. And we notice that the what we've just done here is we've created a form in which I can complete the square on this thing right here, kind of like if I was deriving the quadratic formula. And we just have this a value out in front of it that multiplies the whole thing. But that's also really, really nice because if you notice, this a value is just a constant multiplied by a polynomial term, and that replaces this part of this integrand right here. So I can simply pull the a out in front of the whole thing, rewriting the integrand as 1 over x squared plus b over ax plus c over a. And that's good because now I can just work with this polynomial term x squared plus b over ax plus c over a when completing the square. And this should be noted that we can complete the square by taking half of the term attached to the first order x. And so that's b divided by 2a. We steal this symbol right here. That's x plus b over 2a all squared. And then we had to add and subtract the square of b over 2a to the polynomial, basically adding a version of 0 to get this binomial term. So what we have here is the c over a term, so plus c over a, and then the minus part of the square of this thing, which is b squared over 4a squared. Well, notice that we can find a common denominator for this by multiplying the c over a term by 4a, giving us 4ac minus b squared over 4a squared. And that is a constant. If you notice, this is pretty similar to the quadratic formula. It's like the discriminant part of that, just reversed. And then we also have this squared version of the denominator there, which might be that might show up a little bit later on into this. But in order for this to look the way that we want it to, we want to have some constant which we're eventually going to turn into 1 plus something squared. So it looks like we actually have the constant already, and we have the binomial term squared, including a variable. So that allows us to rewrite the integrand as k over a, the integral of, and then we will have 1 divided by 4ac minus b squared over 4a squared plus, and then we will have x plus b over 2a all squared dx. And notice at this point that this is pretty much the way we'd like this to be. We could very easily do like the arctangent integral with this. We just need to come up with what all the constants attached to this thing are. And then the last thing we need to do here is start doing some substitutions to make our life a little bit easier. So what we're going to do is we're going to set our first change of variables, v, equal to the stuff inside of this squared term. So v is going to be x plus b over 2a. And that makes dv equal to just, of course, dx. So when we do this, this is going to allow us to rewrite this integrand, replacing this business right here with v, and then replacing the dx with dv, which I will write on the integrand. Just a moment. Daddy. Sorry, the baby decided to come visit me. Okay, so far what we've done is we've found our first change of variables, getting this closer to the arctangent derivative. Guess I could write this as v squared and not as the parenthesis v squared, although we will be doing that here in just a moment. So then what I need in order for this to truly be the arctangent derivative, I need to have it where this term is just 1, and then we'll have some constant on top of it, and we'll do another substitution here to get that equal to 1. So it's 1 plus something squared, which is the derivative of arctangent. Okay, so if we multiply both the top and the bottom by the reciprocal of this thing right here, well, the reciprocal of this is just the multiplicative inverse, which will allow me to write this as 1. So we'll have some constant out in front. I'll leave some space for it. The integral of 1 plus, and then we'll have this thing, the reciprocal of this thing, also times v squared. And it might be worth noting here that when I write this inside of the v squared term, make sure I'm not missing anything here, that we'll take the square root of this and v and square the whole thing. So the square root of that bottom part is 4ac minus b squared all inside of the square root. And the square root of 4a squared is just 2a. And that's really nice, actually, because notice that this is kind of like the discriminant from the, that's kind of like the discriminant from the quadratic formula. And we multiplied everything by the reciprocal of this. So we're even multiplying the top by that, but we have the constant multiple rule here that allows us to just take that whole constant to the outside. So we'll write k divided by a times the reciprocal of this thing, 4a squared divided by 4ac minus b squared. Notice that we have an a on top and on bottom. So I can combine this all together as 4 times k a over 4ac minus b squared is the constant on the outside. And then that leaves dv right here. So we can make a second change of variables right here to get rid of this constant so that we'll get the arctangent derivative. So we'll just call this, let's call it t. So we'll set t equal to this thing, which is 2a over the square root of 4ac minus b squared, v. So dt will just be this dv, so 2a over square root of 4ac minus b squared dv. And in order to get this thing over to the side containing dt, so we know what constant we have to multiply by, what we will actually do here is just multiply both sides by the reciprocal of this. So that will make the dv go by itself, which gives me the square root of 4ac minus b squared divided by 2a on the dt side. And then when I change the integrand here to match our new substitution, it will now say t squared, and the dv will now be this thing times dt. This thing is, again, just another constant, so I can write that out in front as the square root of 4ac minus b squared over 2a. And notice that we have some really nice stuff happening here. This term, 4ac minus b squared, is the same as this term, 4ac minus b squared. The only thing that's different is the power. This is the power of 1. This is the power of 1/2. So they can reduce each other so that this is just a square root of 4ac minus b squared on bottom. Then I have a 4 and a 2 that reduce this 4 into a 2. I have 2 a's that cancel themselves. Okay. So if I clean all of this stuff up, I guess what I'm going to do here is clean the top portion of this up. And we'll leave this, but I'm going to like draw a little line there so that I can continue working. And we'll leave the substitutions because I'm probably going to need that to ensure I don't make any mistakes. Okay, so like that right there is in a box. That's the goal. Okay, so cleaning this thing up, we'll have the a's canceling, we'll have the 4 and the 2 canceling, so we'll have 2k on top, and then on bottom we'll have the square root of 4ac minus b squared times the integral of this thing, which is dt over 1 plus t squared. And that, of course, is arctangent. So we get this thing, which is 2k over square root 4ac minus b squared, the arctangent of t. Okay, but t is actually this. So if I replace the t with 2av over the square root of 4ac minus b squared, we'll see that the bottom part of this is 4ac minus b squared. On top, I'll have 2a times v. And that takes care of the t portion of the substitution. So next, I will have the v portion of the substitution and put this back into terms of x. And we should notice here that v is just x plus b over 2a. So v is just x plus b over 2a. But I can distribute the 2a through that term to get this into something slightly nicer. That'll give me 2ax plus b, because the 2a's will cancel each other after that distribution. So I will have 2ax plus b, and there we have it, plus c. And there's the result. Cool. Okay, so why is that an exercise that I wanted to do? Let me get rid of the box. We'll do some examples with this thing. This is 2k over root 4ac minus b squared arctangent of 2ax plus b over root 4ac minus b squared plus c. Well, the reason is a lot of times it seems to me in Cal 2 courses, for example, when we're doing partial fractions, we get a unreducible quadratic. And usually the exercise that I see a lot of students going through is they're actually trying to recreate that entire process over and over and over again for every single question that they're asked. And I think that's a little bit ridiculous, since we can do this in the general case and not have to worry about all of the steps. Okay, so the reason that that I think this is so important is because the Cal 2 integrals involving partial fractions often end up with unreducible quadratics, and I see students going through the motions trying to recreate all of the steps that we just did, and then they have one of the answers, but they get another one and they have to do it again. It's a massive time waster. And I think, frankly, this is an easy enough formula to remember. You just have to make a couple of observations here. So in this formula, let's just observe that the 4ac minus b squared bit, if I were to factor a negative out of it, it would actually say negative times b squared minus 4ac. But that is just the quadratic discriminant. And most people have that memorized before a calculus course. So we could actually just replace that entire thing with the negative discriminant if we use this delta symbol or something of the like. We could even use d. I just don't want to confuse it with the dx part of that for the quadratic discriminant. So what this formula actually says is 2 times the constant that we began with divided by the square root of the negative discriminant for the quadratic, and then the arctangent of 2 times whatever the ax plus b is from the quadratic, and then over, again, the square root of the negative discriminant. So you see that this thing appears in 2 different places. So I think this formula could be written in that way, where we have 2k divided by the square root of the negative discriminant arctangent of 2ax plus b over the negative discriminant's square root plus c. And we see that's actually not a particularly awful formula. So in this case, we just need to decide what our a, b, c, and k are. Well, k is 1. That's great. That just means that this particular portion of that formula is just 2. And then we have a equal to 1, b equal to 1, and c equal to 1. So 4ac minus b squared is just 3. Okay, so we have 2 over the square root of 3. Cool. Then we have the arctangent of, well, we have 2ax plus b. And notice that a is just 1, b is just 1. So that's 2x plus 1 over. And then we have this same square root term that appears here, there, plus c. Boom, done. There's an example. And we have our answer. Now this formula is obviously really powerful. We have another unreducible quadratic here. This is x squared plus 2x plus 4 on bottom and a 3 on top, and we'd like to integrate this thing. So we know what the formula says to do. We're going to have 2 times the constant out here, which is 6, over, and then we'll have the quadratic discriminant, which is b squared minus 4ac. Well, b squared is 4 minus 4 times a times c is 16. So that's negative 12. And then we have the negative version of that. So we're taking a square root of 12, which is actually 2 square roots of 3. But the 6 and the 2 reduce. And then we have the arctangent of. All right, well, the arctangent of 2 times a times x plus b. Well, 2 and a is just 2, and then b is 2. So we will have 2x plus 2 over the same exact discriminant, which is the square root of 12. But the square root of 12 is, again, 2 square roots of 3. And, of course, a lot of the 2's are going to cancel, allowing me to write this as x plus 1 over the square root of 3 plus c. Boom. And we're able to just write the answer down as opposed to messing with all of those steps. So I think this is a really, really cool formula. And I think, frankly, it's useful on like a partial fractions exam or something like that. Because we've done it in the general case, and we know that as long as the quadratic that we're given is like an integer, and they usually are, and the k value is just an integer, and again, they usually are, then we can skip a bunch of the normally really, really annoying steps that we have to go through in order to evaluate something like this and just get on with the rest of the derivative, so the rest of the integral, which you are already doing things like partial fractions and integration by parts for, and this takes up pages and pages of time. So I think this is really cool, and I hope that this helps you.